how your phone instantly knows where you are? That's a GPS, a marvel of satellite tech, math, and relativity. In this video, we'll explore the history of GPS, open up a GNSS module, show how timing and positioning work, and it's something you use every day. Whether you are navigating traffic, calling a cab, or just tagging your location in a photo. GPS began in 1973 as a US Department of Defense project, drawing inspiration from earlier systems like Transit and LORAN. The first prototype spacecraft was launched in 1978, and the full constellation of 24 satellites became operational in 1993. On December 1993, civilian access was officially opened. Originally, civilian GPS signals were deliberately degraded to reduce accuracy, a policy called selective availability. It was removed in 2000, unlocking GPS full power for public use. Key pioneers included Roger Easton, Yvonne Getting, Branford, and math expert Gladys West. GPS works through trilateration. Your device estimates its distance from 4 plus satellites by comparing the precise timestamps sent from space. These satellites carry atomic clocks. GPS needs to be accurate to a billionth of a second. Even 1 microsecond error can throw off your location by about 300 meters. The system also adjusts for relativity. Clocks run faster in orbit and slower in motion. Engineers pre-adjust satellite clocks to maintain accuracy. Without compensating for relativity, GPS system would drift by kilometers each day. It's a real-world application of Einstein's theory. GPS is just one of GNSS constellation. Others included GLONASS, Russia, Galileo, EU's, BeiDou, China's, NavIC, India, QZSS, Japan's. Using multiple systems improves accuracy and reliability worldwide. These constellations work together in modern receivers, giving us faster and more accurate results, especially in challenging environments like canyons or urban cities. Here is a GNSS module supporting GPS, GLONASS, Galileo, and BeiDou. Inside we find RF front-end and SAW filter, quartz oscillator, microcontroller, flash memory. These decode weak signals and provide location data in real time. Some modules even integrate motion sensors like accelerometers and gyroscopes to offer dead reckoning when signals are weak or blocked. In real-world settings, multipath error, signals bounce off buildings, selective availability, removed in 2000 previously caused 100-meter error. Differential GPS, that is DGPS, ground stations correct for errors. SBAS, satellite-based corrections for added precision. DGPS uses ground-based reference stations to calculate corrections in real time, mostly used in marine navigation and surveying. Today, phones use AGPS, combining satellite, cell tower, Wi-Fi, and GNSS for fast and reliable fixes. Hybrid systems help devices lock location even indoors or in cities. Now we can see few myths about GPS. It is working inside tunnels, but it is not. It needs sky view. Weather disputes GPS. No. Even in some conditions, if weather is not good, but still we are getting GPS data. GPS tracks you. No. It's passive. More satellites means better, but only if signals are clear. It's not depends on the number of satellites. It depends on the signal strength. From its Cold War origins to powering aviation, finance, farming and rescue, GPS is the invisible tech guiding our modern lives. Next time you open your Maps app, remember there is a rocket science behind that blue dot. Applications of GPS in daily life. GPS is everywhere. Here are some powerful uses you may not have realized. In aviation, aircraft use GPS for navigation and precision landings. Shipping and logistics. Trucks and cargo containers are tracked globally. Emergency responses. Ambulances and fire trucks reach destinations faster with GPS. In agriculture, tractors use GPS for auto-guided pruning and seeding. In finance, banks timestamp transactions with GPS synchronized clocks. In sports, athletes use GPS to track speed, distance, and performances in real time. As the world becomes smarter and more connected, GPS is becoming the invisible backbone of many critical systems. Not all the GPS modules are the same, and depending on the device, they serve different roles. In smartphones, we typically see integrated GNSS chips like the Qualcomm Snapdragon Location Suite, Broadcom BCM 47755, or MediaTek's Airaha series. These supports multiple constellations like GPS, Galileo, GLONASS, BeiDou, and use a AGPS for fast location fixes, especially in cities. In cars, especially in navigation and autonomous systems, modules like U-blocks, Quectel are more common. These offer higher sensitivity, dual frequency tracking, and real-time correction support essential for lane-level accuracy. Some high-end modules like Broadcom's dual-band GPS chips can even track the signals from two different frequencies, which drastically improves accuracy in urban environments. Different use cases like drones, wearables, or logistics each use tailored modules balancing size, power, and precision. So, whether you are navigating traffic or flying a drone, the GPS inside is optimized for your experience. What the future holds? The future of GPS and GNSS is exciting. Next gen satellites will offer higher precision, better anti jumping, and even authentication for secure tracking. Quantum clocks are being explored to replace current atomic clocks for even better timing accuracy. Crowdsourced corrections may become more common, improving accuracy using phone networks. AI powered positioning will combine GPS with computer vision and sensors to give location even in GPS denied environments. And with satellite constellation like Starlink, we may soon have global backup positioning systems integrated with internet infrastructure. If this video helped you better understanding how GPS works, the tech behind something you use every day, give it a like, share it with others, and consider subscribing. We break down complex technologies into simple stories. So tap the bell icon to explore more with us. See you in the next one.